Lesson 3 of Chapter 14B. It's a lesson on limits. In order to talk about the lesson, I first want to take a trip down memory lane, a little bit of BC calculus. Consider the function that we have here, described piecewise, and suppose we were trying to find the limit, excuse me, as x approaches 0 of f of x. Well, this is a piecewise function, so we have to look at two limits. The limit as x approaches 0 from the right of f of x, which is the limit as x approaches 0 from the right of 2 plus x, which equals 2. And then we take the limit as x approaches 0 from the left of f of x, which is the limit as x approaches 0 from the left of negative x squared plus 2, which is also 2. As a result of these two, we would say the limit as x approaches 0 period of f of x equals 2. Simple as that. Now, the limit from the right has to equal the limit from the left, and if they're equal to each other, it guarantees that the limit is equal to that value. Now, let's take a look at a function f of x and y. And so we have like our Cartesian plane here, and then we have some function above the Cartesian plane, and we may be asking to find a limit as we approach, let's say, this point here. So we might approach from this angle, we might approach from this angle, and this angle, and this angle. And if all those are approaching the same value, essentially we're approaching this point here, if every path that I take towards the point is equal to the same value, then the limit also exists. The problem here is there are infinite many paths. We can take a squiggly path towards that point, and that could go to the point. So what I'm going to talk about here is, in a lot of ways, if we can't algebraically find the limit, we want to prove that the limit doesn't exist by finding two paths that lead to a different limit. Now I'm looking at section 14.2. These are problems straight from the text, from the examples in the back, and let's talk about them. What is the limit as xy, as the point xy approaches, let's say, the point 1, 0, of some function natural log of 1 plus y squared over x squared plus xy, let's say? Well, just like traditional limits, if you can plug it in, you should, and so we shall. So I'm just going to simply plug in 0 for y, and I'm going to plug in 1 for x. And it works. We're allowed to plug those in, and that's the natural log of 1, which is 0. So if there is a limit, chances are you can just plug it in, or you can simplify and then plug it in, and that's really straightforward. Now let's take a look at the next one, number 10. This is the limit as the point xy approaches, let's say, the origin of some function x squared plus sine squared y over 2x squared plus y squared. Okay, so there's no simplification we can do here, and we can't simply plug in the point 0, 0. We would have 0 over 0, which is indeterminate. So here's the strategy. We have to pick paths. Pick paths that pass through 0, 0. So a good path to pick as a starting point is generally a path like y equals 0. So we're going to look at the limit as x comma 0, sorry, a little sloppy, approaches 0, 0 of our expression 2x squared plus y squared. And that's going to equal the limit as x goes to 0. I'm substituting y in, so I have y as 0, x squared over 2x squared, which equals the limit as x goes to 0 of 1/2. Now, limit of a constant is a constant. Okay, so as we approach along the x-axis towards the origin, the function is approaching 1/2. If I'm going to show that the limit does not exist, the goal is to find another path that has a different limit. If I can do that, then I can say the limit does not exist. If I find two paths that lead to the same value, it does not tell me that that is the limit, because there are an infinite many of paths that go through the origin. So you can't prove that it is by proving every infinite path. So anyway, let's take a limit as 0, y approaches 0, 0 of the function, same thing, over 2x squared plus y cubed. That's going to equal the limit as y goes to 0 of sine squared y over y squared. And it looks like we got 0 over 0, so we will employ L'Hopital's rule. The limit as y goes to 0, let's see, this is 2 sine y cosine y, 2 times stuff times the derivative of stuff, all over 2y. And it looks like, well, we can cancel out the 2's, but it looks like we can use L'Hopital's rule here again. So this is the limit as y goes to 0 of, well, we do the product rule. First term, derivative of the second, plus second term, times the derivative of the first, all over 1. And that actually looks like, let's see, let's plug y equals 0. So if we plug y equals 0 in for this, I obviously get 0. But if I plug y in for 0 here, I get 1. So the result is 1 over 1, or simply 1. And there we have kind of what we're after, two different values. And as a result, so therefore, the limit as xy goes to 0, 0 of our function does not exist. So it's pretty easy to prove that something doesn't exist, and that's really going to be our focus. Okay, let's take a look at this limit statement here, and we're approaching again the origin. So I could pick a path x equals 0, and I'm going to dot this a little bit. This is going to be the limit as y goes to 0. If I plug the x is 0 in the numerator, I get 0. Then in the denominator, I get y to the 4th. That's a 4, believe it or not. And this is the limit as y goes to 0. And I simplify this to 0 first before employing the limit, and that comes out to be 0. In a similar fashion, if we let y equal 0, then that's going to be the limit as x goes to 0 of 0 over 2x to the 4th, which is the limit as x goes to 0 of 0, which is 0. So this does not mean that the limit is 0. And there's nothing I can do in the problem to simplify, so the chances are the limit doesn't exist, and we have to find that magical path that shows a contradiction or shows that it doesn't go to 0. So the goal here is, let let's say x equals or let y equals in terms of the other, that when we plug it in, things can simplify nicely. So I'll do this first one for you. Let's say y equals x. So now we have the limit as x comma x goes to 0, 0. 6x cubed y over, it's hard to write on this thing, 2x to the fourth plus y to the fourth. Okay. Actually, what we want to say here, sorry about this, let's put an x in, because the function now is f of x, x. So let's see, let's put an x for y and an x for y. So I'm going to simplify this as the limit as x approaches 0 of 6x to the fourth over, we have 2x to the fourth plus 1x to the fourth, so we have 3x to the fourth. This is good. So this is going to be the limit as x goes to 0 of 3, because that's what it simplifies to. And that would be wrong. Boy, because 6 divided by 3 is always 3. Just kidding. Should be 2. And a limit of a constant is the constant. So there it is. We found, I guess you could say, a contradiction, or we found a violation. So we found a path that yields a limit other than 0, and therefore the limit does not exist. So what was the magic in this? Well, I wanted the degree, the final degree in the numerator, to equal the final degree in the denominator, so that we get cancellation. And that's kind of the key trick strategy. So finally, the limit as xy goes to 0, 0 of the function does not exist. Next one, number 14. Limit as xy goes to 0, 0 of x to the fourth minus y to the fourth over x squared plus y squared. The reason for this example is to show that, yes, the fun with paths and showing that the limit does not exist. But this is a classic example of where the limit will exist, and you just need to use some good old-fashioned algebra. So you can see the top would factor to the difference of two squares. So let me just rewrite this statement. And the x squared plus y squared times the quantity x squared minus y squared over x squared plus y squared. That cancels out to equal this. And now I can substitute it in, and the answer is 0. This one really does have a limit. No matter what path I would take, the limit would be 0. And I've done that by proving by simplification and substitution. Number 18. Limit as xy goes to 0, 0 of xy to the fourth over x squared plus y to the power of 8. Please press pause, work this out, show good notation, and then when you unpause, you will see the answers. We'll check, we'll sing Kumbaya, high five, see you later. Make sure you press pause before I write this, because this is the key. What are we going to let x equal? X equals y to the power of 4. So we have the limit as y to the 4 comma y approaches 0, 0 of, well, let's see, we'll have y to the power of 8 in the numerator, and we'll have y to the power of 8 plus y to the power of 8 in the denominator. So that's going to be the limit as y goes to 0 of y to the 8th over 2y to the 8th. I guess I showed an extra step here, which is the limit as y goes to 0 of 1/2, which equals 1/2. Therefore, the limit does not exist. Two different values. Two different paths leads to two different values. The limit does not exist. One more example, which is a supplement to the textbook. And here we go. This is a pretty traditional polar transformation problem. When you see x squared plus y squared, we can make a polar transformation, and instead of saying the point x, y is going to 0, 0, we can say that through this polar transformation, r, the distance from the origin to the point x, y, is actually decreasing to 0, collapsing to 0. So through our polar transformation, x equals r cosine theta, y equals r sine theta, and of course x squared plus y squared equals r squared. This limit becomes, instead of, again, x, y going to 0, we say r approaches 0 from the right. We're talking about positive r, and so r is collapsing. The distance from any point to the origin is collapsing. So then we make our polar transformation. So this is going to be the cosine of r squared over r squared. Looks like we can use L'Hopital's rule here. So the limit as r goes to 0 from the right, please don't forget from the right, and geez, what is that going to be? Negative sine r squared times 2r over 2r, which is the limit as r goes to 0 from the right of negative sine r squared, and that goes to 0. And we've successfully found the limit. Let's try that same procedure for number 40 in the textbook. Looks like this. Limit xy goes to 0, 0 of x squared plus y squared times natural log x squared plus y squared. Now that looks like a real hot mess. Anyway, press pause, try this out, and check the answer. Equals the limit as r goes to 0 from the right, r squared times natural log r squared. And this is more of a lesson L'Hopital review. As r goes to 0 from the right, we're going to write this natural log r squared over 1 over r squared, so that we have infinity over infinity. So now we have the limit as r goes to 0 from the right, 1 over r squared times 2r, that's the derivative of the top, and the derivative of the bottom, negative 2 over r squared. We got some simplification here. The limit as r goes to 0 from the right of 2 over r times r cubed over negative 2, and that leads to the limit, still simplifying here, as r goes to 0 from the right of negative r squared, which also equals 0. Great. So if the limit exists, there's some kind of algebra, there's some kind of substitution directly from the algebra, or there's this polar transformation. If it's not one of those, then the limit won't exist, and you have to find paths that lead to different limiting values. That's the end of the lesson, and the only thing left for me to do here is to give you the homework. And the homework is from section 14.2. There's a whole bunch of limit problems from 5 to 22. Pick some of them. We did some of the even ones for the notes. You pick some of the odd ones or some of the even ones and see if you can find the limit. Also pick some from 39 to 41. I believe those are the polar transformation. And finally, look at number 37. That's going to require you to kind of put together the concept of continuous at a point. Continuous at a point on the Cartesian plane. And ties together a concept from last year to this year. You might just want to read up on the continuity in that section 14.2. Anyway, hope you enjoy. Goodbye.